We defined expectation last time, and we said expectation is linear. In fact, we showed it. Expectation is a linear operator. What does that mean? Expected value of a times x plus b, where a and b are constants, constant real numbers, is always a times expectation of x plus b. Okay, just follows from the definition, and we proved it last time. Now, variance is another moment that another quantity that we defined last time. The variance of a random variable x was defined to be what? You remember? Variance of x was defined to be expected value of x minus expected x squared. Okay? An alternative expression for variance is expected value of x squared minus expected value of x squared. Okay, let's just show that this is true. Let's show that this is equal to the other. Well, it's easy to do that. What would you do? Just compute the quadratic expression here. Expected value of x squared minus 2x expected x plus expected x squared. What's next? Q-shot. What's next? What do you mean? Use some fact about expectation. What is this fact? Expectation is linear. Here inside the parentheses we have a sum. Okay, this sum of terms can be, the expectation of the sum of terms can be broken up into the sum of the expectations of each term. Okay, so let's do that. Expected value of x squared. Please follow this very closely. Okay, this is the only time probably that I'm going to do this in such detail, and you will be expected to really know this like the back of your hand. Okay, so let's do this. Expected value of x squared minus expected 2x expected x plus the expected value of x squared. Now what? Well, this one is a good sign. This one already exists in this alternative expression. So we got that. How about this one? Expected value of x squared. Yes, please. Right, because expected value of x is a constant. It's not random. The expected value of a constant is the constant itself. How do we know this? We know this implicitly from here, right? Expected value of ax plus b is expected value of ax plus expected value of b, but expected value of b is just b itself. Why? Because b is equal to b with probability 1. Okay? So the expected value of a constant is the constant itself. Let me write here. This is a constant. So the expectation is equal to the constant itself. What do we do about this term? Again, expected value of x is a constant. Right? What happened? 2 is a constant as well. Okay, so what happens? Let's look at this. Expected value of ax is a times expected x, right? Set b equal to 0. Expected value of a constant times a random variable is equal to the constant times the expectation. So constant comes out of the expectation. So this is negative 2 expected x times, what do we have left inside the expectation? Expected value of x. Oh, you're right. Expected value of x itself. Right. So are we done? Yes. This is equal to expected value of x squared minus expected x squared. And this is an you can think of this as an alternative definition of variance. And sometimes it's more convenient to use this one than this one. Okay? In fact, more often than not, this is more convenient. Any questions? Okay. On the other hand, variance is not linear. Okay? Let's show this. In fact, let's show what happens when we want to compute the variance of ax plus b. I would like to use this definition of variance, this expression for variance. Let's write it down. Variance of ax plus b is the expected value of ax plus b squared minus expected ax plus b squared. Right? This is easy. We can just write this down. This is the square of what is expected ax plus b? A times expected x plus b. So take the square. That's it. There's a negative sign in front. Now we need to expand the inside of this expectation in the first term. Ax squared plus what? 2abx. Right? Oh, thank you. A squared expected x, a squared x squared plus 2abx plus b squared. Now what do we do? Use the linearity of expectation in the first term. This breaks into, well, a squared comes out of the expectation. A squared times expected x squared plus 2ab expected x, right? What else? Plus expectation of b squared is b squared itself, because b is a constant. Okay? Are you following? Okay, I can ask random questions. Okay. So, what do we do here? Let's ask you. Yeah, what do we do here? Ax plus, right. Right. Okay. Okay, now we have a lot of terms. And we're sort of done by using the linearity of expectation. So what do we do? Let's do, this is the fun part. Okay, so tell me, Kürşat. This guy cancels this guy because of this negative sign. What else? No. This guy cancels this guy because of the negative term. So we are left with a squared times, maybe group these two terms, expected x squared minus expected x squared. Do you recognize this from somewhere? You? What's your name? Tuğçe, yes. So, yes. So we have a squared times variance of x. And we're done. What did we show? Exactly. That's one of the things we showed. The constant b does not make a difference. So first of all, set a to 1. It's like we don't have an a. Variance of x plus b. Set a to 1. Variance of x plus b. What is it? Variance of x. So adding a constant to a random variable does not change its variance. Does that make sense? Think about the PMF. What happens to the PMF if you just add a constant to all the values? The PMF just shifts. The expectation just shifts. And the difference, the spreading of the PMF around its expectation stays the same. Okay? So adding a constant has no effect on the variance. That's number one. Number two, if you take a random, now set b equals to 0. B is 0. Multiplying a random variable by a constant scales the variance by the square of that constant. Okay? So if you multiply the random variable by 2, the variance will be 4 times the original variance. If you multiply the random variable by -2, again the variance is 4 times the original variance. What is variance measuring? Variance is measuring how spread out it is. And when you take a distribution and multiply all the terms, all the values in the support of the distribution by 2, okay, the square of the mean difference, in fact the mean of the square difference from the mean is scaled by 4. Okay? Okay, this is really important to know. And it will be useful in a lot of problems that we do. So as an example, let's derive the mean and the variance of the Bernoulli random variable. And then I'll leave as exercise to you the discrete uniform and the Poisson. Okay. Where's the eraser? So what do you think is the expectation of the Bernoulli? Is Bernoulli P. How many parameters does the Bernoulli distribution have? 1 parameter. So if X is Bernoulli with P, you tell me expected value of X is. How about you? You. Okay. You then? Really? Too bad. So I don't know. Anyone to remind us? What? 0 point what? 1 or 0. So X is 1 or 0. What is the definition of expectation? Let's remind our friends. Watch closely. Expectation of X is summation X times Px of X. What is the small script x? It goes through all the values that the random variable x can take. Let's just say all x here, if you want. Anyway, let's just say all x. In the Bernoulli distribution, Bernoulli random variable takes 2 values. It's either 1 or 0. So it's 1 with probability p and 0 with probability 1 minus p. So expectation turns out to be p. Okay? Any problem? Okay. You weren't absent today, so you can tell me the variance. Variance of x. know, the definition maybe. How about the definition that we just proved? Expected x squared, right, minus square of expectation. Okay. Now, what do we know? We already know this. This is p squared. Okay, we need to compute the expectation of x squared. Okay? We can do this by treating x squared as a new random variable, right? X squared takes how many values? You in the back. 2 values. 1 or 0, right? Because if x is 1, x squared is 1. X is 0, x squared is 0. X squared is 1 with probability what? Who said 1 over 4? It's a nice contribution. Thank you. But the parameter is p. We haven't given a value to p. Okay, if p was 1 over 4, that would be perfect. So it's 1 if x is 1. X is 1 with probability p, so this is 1 with probability p. X squared is 0 then with probability what? 3 over 4, right? Which is 1 minus p. Okay. So in that case, expected value of x squared is, surprise, it's p. Okay? Bernoulli random variable is very simple. If you square it, nothing changes. So its expectation, of course, doesn't change. So this is p. So we have p minus p squared, which is p times 1 minus p. It's nice. It's also, think about it, it's really quite beautiful maybe, because Bernoulli p random variable and the Bernoulli 1 minus p random variable have the same variance, which makes a lot of sense. Okay, so think of a coin with bias 0.9, okay, and think of a coin with bias 0.1. They have the same variance. Okay, you can close the window if you want. You're in a draft, maybe. It's up to you. I just said feel free to close the window. So what's the next question? The next two are exercise for you, but let's do them partially. Okay, the first one is the mean and variance of discrete uniform random variables. So let's do the mean. Okay, so x is discrete uniform. How many parameters? 2. What are they? The beginning and the end, right? The beginning and the end. Okay, it takes values between a and b, takes values, it takes all possible integer values in that range, a and b included, with equal probability. So the expected value, use this expression, summation, let's say k times px of k. And k goes through integers from let's think. What are the values that x takes? A to b. Okay, a plus 1, a plus 2, up to b. A to b. So that's it. This is the expectation. What is px of k? 1 over the number of values. 1 over b minus a plus 1. Okay, by definition, b is bigger than a. Okay, so let's do this. Summation k times a constant. Maybe let's put the constant out of the summation. 1 over b minus a plus 1 summation k, k from a to b. What is the summation? A plus b times what? B minus a 1 over 2. Okay. A plus b. Remember how Gauss did this right at school when he was 10 or 12? That's the story. A plus b times b minus a plus 1 divided by 2. Okay, so this cancels with that. And we're left with a plus b over 2, which we could have kind of guessed from the beginning. Why? Because we know that expectation is a center of gravity of the PMF. So if this is A, this is B, expectation of this distribution should be right at A plus B over 2. Okay? This is no surprise. Show that the variance of x is, let's say, b minus a squared over 12 as exercise. Okay, show this. Okay, let's not spend all of our time on this. Let's also quickly go through the Poisson. Remember, when I introduced the Poisson distribution to you, I said, you know, it may look kind of complicated, but it's going to have really nice properties, especially a really nice expectation and variance. Okay, now this is the time to fulfill that promise. If x is Poisson with parameter, how many parameters? One, just one. Remember, ugly looking PMF, really nice. Poisson with parameter lambda. Okay, so what is this PMF? Okay, so let's write the expectation. Expected value of x is summation k px of k. K goes from, let's say, negative infinity to infinity because it takes integer values. We can write this over all integers. However, the PMF is defined actually only on the non-negative integers, right? So when we write px, when you substitute the value of px of k, the summation will start from 0. What is the what is this expression for px of k? Lambda to the k, e to the minus lambda over k factorial. So what do we do? First thing you may realize is that there's a k here, and the first term is 0. So the first term effectively goes away. This summation actually starts from 1. K, in fact, and the k and k factorial cancel to give us k minus 1 factorial. Lambda to the k, e to the minus lambda. Okay, this is the first manipulation we do. Next, we can put e to the minus lambda out of the summation and maybe put one of the lambdas out of the summation to get lambda to the k minus 1 over k minus 1 factorial, k going from 1 to infinity. But this is no different from saying, this is the same as saying k going from 0 to infinity, lambda to the k over k factorial. Okay, I just, advance the terms by 1, which happens to be Taylor series expansion of e to the lambda. Okay, so we get e to the minus lambda times e to the lambda times lambda, which gives us lambda. So the expected value of a Poisson with parameter lambda is lambda. Just like the expectation of a Bernoulli with parameter p is p. Okay, really nice. So when you compute the variance of x as exercise, you will again use the same trick, maybe a little with a little more manipulation. Okay, and the variance will turn out to be also lambda. Okay, any questions? Let's erase this part. If there are no questions, we can move over to the next topic, which is joint PMFs. Okay. I think we've talked enough about one random variable and its PMF. Okay. So let's turn our attention to two random variables living on the same sample space. Okay. Often we are faced with such situations. Okay, example, we receive two signals as a result of two different radar measurements. Okay. Or you have a group of network routers. Okay, at each there is a certain load, and these loads are modeled as random variables, and you are interested in their joint statistics, joint behavior. Or, maybe meaning more to you, your grades received from two consecutive exams. Okay, so, okay, in all of these cases, for x and y, to have a joint PMF, meaning the probability that x is equal to x and y is equal to y at the same time, obviously, x and y have to exist on the same probability space. Okay? The same probability law, we are examining this event under one probability law. Okay? So let me repeat. The probability that x is equal to x while y is equal to y is the joint PMF. It's abbreviated as PXY, XY, okay? So, what does this mean? Now, as you know, AND means intersection. The probability that x is equal to x, intersection y is equal to y. So, intersection of two events, okay? When we want to compute the probability that x and y are jointly in some event A, what will we do? How can we write this in terms of the joint PMF? Let's try to do this. The probability that x and y is in A. Write this in terms of the PMF. The joint PMF. So, if I can split A into its individual elements, okay, individual outcomes, of course, in this case, A contains elements like tuples, right? Pairs of values. Okay, so this would be a summation of the probability that x is equal to x1, y is equal to y1, or yi, where xi, yi are elements of A, and this summation is taken over all such xi, yi pairs, okay, in A. In other words, what is this? This is pxy joint PMF xi, yi. So the only difference of the joint PMF from the earlier PMF that we defined is this has 2 arguments. The other one has 1 argument. Obviously, you can generalize this to any number of arguments. Okay. Now, let's see if we have an example. Let's do an example before we talk about marginals. Let's look at this example. Yes, please. Probability mass function, as we defined last time. Okay. Now, the 2 random variables x and y have the following joint PMF. Okay, why are we tabulating this? Because it's 2-dimensional. Okay, it's easy to put these values on a table. So let's answer the following question. By the way, how do we read this table? This entry, 0, is the probability that x is 1 and y is 1. Okay? This 1 over 10 is the probability that x is 2 and y is 1. The probability that x is 3 while y is 1 is 2 over 10. Okay? What is this probability? The probability that, yes, y is 3. Okay, so everybody now knows how to read this table. Now, what is the probability that x is less than y? X is less than y. So it's just like this event A that I used over here. In the event A in the example is the event x is less than y. So I'm summing overall x, y in A. X, y pairs such that x is less than y. Pxy, xy. Okay? In other words, sum all the probabilities of the pairs in which the x component is less than the y component. Okay? So let's sum them. What are they? So if you draw the diagonal, below the diagonal, x is less than y. Below the diagonal, we have 3 terms. 1 over 10 plus 2 over 10 plus, again 2 over 10. Okay? Any questions? 1/2. By the way, the numbers in the table need to sum up to something. 1. Right. Okay. Why? Because the probability, these are all the possible values that the pair xy can take. All those probabilities have to sum up to 1. So summation pxy xy over all xy values should be 1 in order for this to be a legitimate joint PMF. How about column sums? What is the first column sum? What does that mean? The sum of the first column is the sum of pxy xy over all x or all y when x is equal to 1. This is the sum of the first column. Let's think what this is. What does this say? This is the probability that x is 1 and y is anything. In other words, this is the probability that x is 1, right? Because it goes through every possible value that y can take while x is 1 and sums up all of those probabilities. This should give us the probability that x is 1. In other words, the marginal PMF of x at 1. We call this the marginal in order to distinguish it from the joint PMF. Okay. So in general, if you look here, the marginal PMF of y can be found by summing over all x, pxy, xy, the joint PMF, while keeping the value of y fixed at that value of small y, script y. Okay? Just comes from the definition of probability. Also, let's look at this again. Px of x. Okay, if you sort of still are not convinced by this, here's a repetition. So this is the time to pay attention. Px of x is the probability that x is equal to x. Okay? This is the probability of the event that x is equal to x. It is also the probability of the union of all events, x is x and y is y, over all possible values of y. Okay? But these events are disjoint events, so we can sum their probabilities. But their probabilities are simply the values of the joint PMF. Okay? So, in other words, you can find the marginal PMF of x by taking the joint PMF and summing over y. Okay? And you can find the marginal of y by taking the joint PMF and summing over x. Okay? So to finish this problem, let's compute the full marginal distribution of x. Px of 1 is 1 over 10 plus 2 over 10, 3 over 10, right? And Px of 2 is Px of 2, 1 over 10 plus 1 over 15 plus 2 over 10. Okay, so this is 2 over 30, 3 over 30, and 6 over 30. So what? 1 over 15? 4 over 15. Okay. Px of 3 is 2 over 10 plus 1 over 30 plus 1 over 10 equals 10 over 30, which is 1/3. Okay, any questions? Let's write this again. Px of 2 is 1 over 10 plus 1 over 15 plus 2 over 10. So this is 6 plus 3, 9 plus 2, 11 over 30.